Hello everyone. Today we'll be learning about velocity-time graphs and how to describe motion in terms of acceleration. We'll also be learning how to read acceleration from velocity-time graphs, in the same way that we learned to read velocity from displacement-time graphs in the last section. Now, a plot of an object's velocity over time is called, as you might expect, a velocity-time graph. We can see one of those over here. As always, we have the time on the x-axis because it's the independent variable in all situations. The object's velocity is measured in meters per second on the y-axis of the graph. Because it's a vector, it's important that if the velocity's direction is not obvious, you should put it on the graph. Velocity is measured relative to a stationary frame of reference. We've learned a little about this before. The stationary frame of reference is assumed to have a velocity of 0, and so everything else moving is measured with a reference to that frame as being stationary. Let's take a look at a velocity-time graph. We can see here an animation. So, as the car is moving from a velocity of 0 to this velocity up here, we could see that it was speeding up. When its velocity is fixed at a certain position, the car moves at the constant speed, but as it moves down to the bottom, it slows down and eventually stops. So once again, we can see that when the slope is moving upward, the car is slowly getting faster. When it's flat, it's moving at a constant velocity, because the velocity, which is on the y-axis, is constant when the line is flat. Now, let's consider an interval of time on the x-axis, delta t, which we can see at the bottom here. The area of the rectangle underneath the graph is the product of v and t, because we can see that the height of this rectangle is given by v, the velocity, and the length of the rectangle is given by delta t, the interval on the time axis. And so we can see the area is v times delta t. Now we know that already from our previous studies that the velocity of an item is delta r over delta t. So substituting this in, we can see that v delta t is delta r. It's pretty obvious to see that as soon as you multiply delta t by, you multiply both sides by this delta t at the bottom. And so the area underneath the graph, v delta t, actually gives you the displacement of the object. And so just by examining the area underneath the velocity time graph, we can tell how far the object has moved. We can see that the units work out as well, because velocity is measured in meters per second, and time is measured in seconds. So multiplying meters per second by second, we end up with meters, which is the proper unit for displacement. Now when the velocity is less than 0, the object is moving backwards. So in this first part of the graph, the object has a positive velocity, so it's moving upward. But in the second part of the graph, it has a negative velocity. And if upward velocity is positive, then negative must be downward velocity. So in this section of the graph, the object is moving upward, and in this section, the object is moving downward. Now when we calculate displacement, we have to subtract the area that's underneath the graph in order to find the final displacement, because this will be the object moving up, the other will be the object moving down, and so it will be moving backwards and moving back toward 0. And when the areas above and below the axis are equal, the object must finish when it started. So for example, in this picture, this area under the graph is given by the area of the triangle, and it ends up being 2.5 meters, and that's upwards. Whereas this is also 2.5 meters, and that's downwards. And so in this graph, for example, we can see that the object moves 2.5 meters upward and then 2.5 meters downward, which means that it must end in the exact same position as it started. So, when an object is going forward, is speeding up, the graph has a positive slope. So we can see that in this graph, for example, the object is speeding up as its velocity is moving from 0 to 10. When the object is slowing down, on the other hand, like over here, the graph has negative slope. So its speed is going down from 10 all the way down to 0, and the slope is negative. When the object is stationary, or if it's moving at a constant speed, its graph is flat. So if the line were to just lie across here, it would be an object that's not moving at all. If it's flat but it's all the way up here, the object must be moving at 10 meters per second. So unlike displacement time graphs, a flat line can still indicate a moving object on a velocity time graph. Now, the rate at which an object's velocity changes over time is called its acceleration. You've probably heard this word before, but not in the terms of that physics knows it. So, acceleration is a vector quantity, which means that, of course, it has direction, and it is measured in meters per second squared. This is the same as meters per second, and so it measures the speed change in a number of seconds. If an object's speed is changing at 1 meter per second, then its acceleration is 1 meter per second, or 1 meter per second squared. It points in the direction that the velocity is changing. And that might seem a bit incongruous with your previous ideas of acceleration, because if velocity is changing, that doesn't necessarily mean that an object is speeding up. Now, whenever an object's velocity is changing, it is accelerating. This is always true, don't forget it. Outside of physics, we usually assume that an object that's accelerating is speeding up. But in physics, this isn't the case. In physics, an object that is slowing down or changing direction is having its velocity changed. And so these objects are accelerating as well. Even if an object's speed doesn't change, but its direction of velocity changes, it is accelerating. Now, when an object accelerates in the same direction it's moving, it speeds up. So we can see, for example, in this animation of an apple, when the object is falling back down, it's accelerating downward due to gravity. And so when it's moving down, it starts slow, and then it speeds up as it moves in the same direction as the acceleration. On the other hand, when an object is accelerating in the opposite direction it's moving, it slows down. Now, when the apple in the animation is moving upward, it's being accelerated down by gravity. And so we can see that it's actually starting fast and getting slower as it reaches the peak of its trajectory. If an object accelerates in a different direction, it changes direction. So we can imagine, for example, an apple being thrown off into the distance. So when we start throwing it, it's moving in that sort of direction, up there. As it accelerates downwards, it eventually reaches the top of its trajectory and starts moving downward again. And so we can see that it's accelerating downward, and this is changing the direction of its velocity. Now, just like velocity, the acceleration of an object is rarely constant in the real world. There are no corners in graphs in the real world if you look close enough. They're always curved. So an object's instantaneous acceleration, like its instantaneous velocity, can be found by drawing a tangent to the graph and then finding the slope of the tangent. So at this point, for example, the slope of the tangent shows the instantaneous velocity of the object whose velocity is given by the green line. An object's average acceleration, on the other hand, is the slope of a chord between 2 points. So if we wanted to know this object's average acceleration over these 5 seconds, we would draw a chord from this point to this point, and the slope of this blue line would give us the average acceleration that the object experiences over these 5 seconds. Now, let's take a look at an example. A moving car slows down and stops briefly at a set of traffic lights. So we can see that the car here is moving. When the slope is moving downward, the car is slowing down. When we reach 0, and the car has 0 velocity, it must be stopped. After 10 seconds, the light goes green, and the car speeds up again, and its velocity steadily increases from 0 up to 15 meters per second. So, looking at the slope, we can see that it started with a velocity of 10 meters per second. So there's the starting position. It then slowed down with an acceleration of 2 meters per second backwards. 2 meters per second backwards means that it was experiencing acceleration in the direction opposite to which it was moving. And that means that we have a negative slope over here. Looking at the rise over run, we can see that the rise is minus 10 meters per second, and the run is 5 seconds. So dividing 10 meters per second by 5 seconds, we get 2 meters per second, or 2 meters per second squared. Remember, the direction is backwards because the car is slowing down. when we look at how it speeds up again, we can see that the rise is 15 meters per second. The run is still 5 meters per second. And so the slope is 15 meters per second per 5 seconds. Evaluating this, we can find that the acceleration is 3 meters per second squared in the forward direction. This ends the theory. Today we've learned about velocity-time graphs and how to determine both the displacement and the acceleration of an object from a velocity-time graph. We also talked a bit about acceleration in general. Let's go on to some questions. Question 7. True or false? A car that is speeding always has very steep slopes in its velocity-time graph. Well, let's take a look at a velocity-time graph and see what it says about an object's motion. The following car is speeding. It is moving at 120 kilometers per hour, which obviously is above the speed limit, and the line is flat, which means that its speed is constant at 120 kilometers per hour. So we can see that even though there are no steep slopes in this graph at all, the car is still speeding. And so we find the answer to this is false. In a position time graph or a displacement time graph, a sharp line means that there's a high velocity. So in that situation, a steep slope would mean it was speeding. But in a velocity time graph, even a flat line can be moving very fast. Question 7, part B. True or false? A slope of 0 in a velocity time graph means the object is not moving. Well, let's take a look at a velocity time graph. So here we have a velocity time graph, and we can see that at this point, indeed, the object isn't moving. But this is because we have a velocity of 0. That is, we're at the x-intercept. And in fact, at all the x-intercepts of a velocity time graph, the velocity is 0, so the object isn't moving. But if we look at this part of the graph here, we can see that the slope is 0, but the velocity is about almost 10 meters per second. So we can see that here the slope is 0, but the object is still moving. However, the object is not accelerating. That's what it means when the line is flat. But we can see that the answer to this question is in fact that it's false. Because even though the graph has a 0 slope, it's still moving. Question 8. At the marked point, that is here, what can we deduce about this car? Well, let's go through the options, shall we? D. It is moving very quickly. Now, when we look at the velocity of a thing, we can say how far away it is from the x-axis. And so at this point, this mark point here is very, very close indeed to the x-axis. So in fact, the car is moving very slowly. So D can't be the right answer. All right, what about C? It is south of its starting position. Now remember, to find out this, we need to know its displacement. And its displacement is the area underneath the graph. So we can see that in the first part of the graph, it moves forward that area, that amount. Whereas the second part of the graph, it doesn't quite manage to move that amount. And so it's still further northwards than it is southwards. And this means that it is in fact north of its starting position and not south. That means that C is wrong. Alright, what about part B? It is speeding up. So we start off at about 5 meters per second in the opposite direction, so velocity south, and we're getting close to 0. So we're not in fact getting faster. The slope is positive, but because our speed is already going south, we're slowing down rather than speeding up. And so it can't be B. What about A then? It is accelerating. Isn't that the same thing as B? Well, no. Accelerating means that its velocity is changing. And we can see that because the slope here isn't 0, it is accelerating. And although it's getting closer to the x-axis, so it's slowing down, it still counts as accelerating. So the correct answer is A. Remember that even if an object isn't speeding up or slowing down, it can still be accelerating if its direction is changing. Question 9. Draw a qualitative graph of an apple's velocity after it has been tossed up into the air. Well, let's think about this. As soon as the apple leaves our hand, it'll be moving quite fast upwards, but then it'll slowly get slower and slower and sort of stop for a moment, and then fall back down until we catch it. And so, on a graph, it would look something like this. We start off with a fairly large velocity upwards, which gets smaller and smaller as the gravity acting on the apple slows it down. Eventually, the apple stops moving upwards and starts moving downwards instead, and it gets faster and faster as it falls toward the ground or toward our hand. Question 10. Draw a qualitative graph of a person pacing back and forth across a room. Well, let's start off with the axes, shall we? We'll say that we're moving forward and back across the room, rather than left or right or up or down, because that's easier to think about. So, on our y-axis, we have our velocity forward in meters per second. Of course, as always, our x-axis is the time, because time is always the independent variable. Alright, so suppose we start walking forward across the room. We're moving at a fairly constant velocity, because we won't be suddenly breaking into a run or anything like that. So, we'll have a flat line at a fairly constant velocity like that. So starting from zero velocity, we quickly start moving forwards. It's a fairly fast acceleration, and end up at this constant velocity. Now after this, we have to turn around and walk in the other direction. So assuming we turn around fairly quickly, we'll accelerate into the opposite direction until we're walking backwards. And so that will give us a flat line underneath the x-axis, meaning that we're walking backwards. And then we can sort of continue this, walking forward and then back across the room until we get tired and think of something else to do. Question 11. Draw the displacement time graph of an object with this velocity time graph. Now remember, the velocity of an object is given by the slope of the displacement time graph, and the displacement of an object is given by the area underneath the velocity time graph. So we can see that at this point, the object's speeding up, and so the displacement will be positive. When this reaches a flat line, the displacement will be going up by a set amount. It will be going up linearly because the velocity isn't changing, so the slope isn't changing. When we start moving the opposite direction, we're still positive velocity, and so we're still moving forward. Here we have to stop, and suddenly we're in negative velocity, so we're moving back again. And once we've worked all this out, our final graph looks something like this. So we can see that at this flat point of the graph, we're moving up linearly without curving. When our velocity reaches zero, our slope here is zero, because of course the slope of this graph gives you the value of this graph. Here we start speeding up in the other direction, until we get to this point, and here we stop speeding up and start slowing down. And so this means that this graph is curved this way. When we reach 30 seconds, you'll notice that the area in this part of the graph is greater than the area in this part of the graph. That means that our displacement is still positive, so we don't get back to our starting position. The only way we would get back to our starting position is if the area in the second part of this graph matched exactly the area in the first part of the graph. Because of course the area above the x-axis cancels out the area below the x-axis. Finally, question 12. And we have a multi-part question here with this velocity time graph. What is the velocity of the car at the start? So initial means that we're looking at time equals 0. And time equals 0, we can see that our green line here starts at 10 meters per second. And so we assume that our velocity is in the same direction that the car is moving, so we can say forward. And because that's fairly obvious, we don't need to include a direction here. Part B. What is the acceleration of the car between 0 and 20 seconds? Well, remember, to find the acceleration of something, we can find the slope of the velocity time graph. So, to find the slope, all we need is rise over run. So we can draw a little triangle here, in which our rise is 30 minus 10, so that's 20 meters per second. And our run is this x value over here, so that's another 20, and that's in seconds. So dividing our rise, 20 meters per second, over our run, which is 20 seconds, we end up with 1 meter per second, or 1 meter per second squared. Now, part C. What is the acceleration of the car between 50 and 60 seconds? Well, once again, we can use rise over run to find the slope. So our rise, this time, is not positive, but negative, because the slope is downward. So our rise is 30 meters per second. And our run from 50 to 60 seconds is, of course, 10 seconds. So dividing the rise, minus 30, by the run, 10, we end up with an acceleration of minus 3 meters per second. Because there's a minus, we assume that the direction is the opposite to all the positive directions we've been working with so far. So that means that it's 3 meters per second backwards. Finally, part D. Find the displacement of the car after 60 seconds. Now remember, to find the displacement of something using its velocity time graph, all we have to do is find the area underneath the graph. And so with these dotted lines, we can easily divide the graph into 3 different sections. The trapezium on the left, the rectangle in the middle, and the triangle on the right. Now let's start with the trapezium. To find the area underneath the trapezium, the area of the trapezium rather, we can take the width of the trapezium here, which is 20, and the 2 altitudes, which are 30 and 10. Now remember, the formula to find this area is 30 plus 10 on 2, so that's the 2 altitudes divided by 2, multiplied by this width here. And so, evaluating this, we find that 30 plus 10 is, of course, 40. 40 divided by 2 is 20. And so we end up with simply 20 times 20. This 20 is in meters per second, and this 20 is in seconds. And so we end up with 400 meters. And the second and the per second cancel out. The next part of the graph is a little bit easier. It's just a rectangle. Now to find the area of the rectangle, all we have to do is multiply this width, which is 30 seconds, by this height, which is 30 meters per second. And of course, 30 times 30 is 900. The second cancels out with the per second, and we end up with just 900 meters. Finally, we have this triangle. Now, the altitude of the triangle is 30 meters per second, and the base of the triangle is 10 seconds. So with our old formula, half base times altitude, we find that base times altitude is, of course, 300. We can divide that by 2 to find the area of the triangle, which of course ends up being 150 meters. So to find the total area under the graph, all we have to do is add all these parts together. So we get 400 meters plus 900 meters plus 150 meters to get 1,450 meters. And this is the total area under the graph. It's about 1.5 kilometers. And that means that over these 60 seconds, this car traveled 1.5 kilometers or thereabouts, and its velocity looked like this the whole time. This concludes the section. Today we've learned about velocity time graphs, as well as how to describe motion with acceleration, how to measure acceleration and displacement of velocity time graphs, and how to draw our own.